Yes, so I think my job was to give you a skeptic's view of community structure. So that's what I'm going to do over the next couple minutes. And the title of my talk is Community Structure and Networks, Static, Dynamic, and Multimodal Approaches. So here's the outline of roughly what I want to do over the next couple minutes. The first thing, in order to be skeptical about an idea, first you have to understand what the idea is, right? So we'll talk a little bit about what community structure actually is. Then we'll move into common methods to detect community structure in static networks, which means single instances of a network. Then we'll move into methods for detecting dynamic community structure in temporal networks. So that's when you have a series of networks in a row. Then we'll move on to extensions to multimodal data. So what if we don't just have networks in different time windows, but we have networks from completely different imaging types, say functional connectivity and structural connectivity, for example. After that, we'll talk about methods, specifically how do I do it right and what should I be thinking about. And for much of that, I'm going to be giving you some references that you can feel free to look up afterward. I'll give you the idea, but if you want to dig in detail, I'll have the references all there as well. And then I have a page for code. So if you want to actually apply this to data, where's the code to get started? So that's what we're going to do. So first, what is community structure? So community structure is the technical term in network science for clustering or modular organization in a graph. And an illustration of that is given here, where you see actually a network of Caltech Facebook friends. So every dot is a person at Caltech. They're connected if they're friends on Facebook. And so what you can immediately see from this network is that there's really strong clustering structure, meaning that there are groups of individuals who are densely interconnected with one another, and then another set of individuals who are densely interconnected with one another, but there may be either complete white space between them or maybe a few very sparse connections between them. So that clustering structure is what we refer to as community structure. It's one sort of mesoscale organization in a graph. What are some other mesoscale organizations that you might have heard of before? You may have heard of Ripch Club organization or core periphery structure. Those are both two other kinds of mesoscale organization. Community structure is one that really focuses on understanding modules inside of the data. So community detection tools are technically clustering tools for network data. So why wouldn't you just use ordinary clustering tools for this problem? Well, the reason is that networks actually have very interesting structure often that's different from other types of data. And so community detection tools are tuned to optimize their detection procedures on the kind of data that networks are. So that's why you would do that. Okay, so then the question is, if community structure or community detection algorithms are a way of identifying modules in a network, why would we want to do that? Why is that an important question or an important feature of the data? And the answer is that modules appear to be substrates for functional segregation. They enable you to separate out regions of the brain that may be performing one function separately from another function, but they're also really important substrates for behavioral adaptation and learning. So the idea that modularity is an important fundamental characteristic of adaptive systems has been around for decades, even centuries, even longer than that, if you go back through history. So I have a picture up at the top here of Darwin finches, where the modularity of structure is known to be supportive of the evolutionary changes that enhance diversity over the years. Modularity of mind is another common idea. I'm thinking particularly of Jerry Fodor's book called Modularity of Mind, which was written in the 1980s, suggesting segregation of function in the brain. But finally, we can actually make all of those ideas a little bit more concrete by studying network organization and identifying where the modules actually are. So how do we do that? Well, we can do that in a couple different ways. Even over the last couple talks, you've seen community structure shown in a couple different ways and with different sorts of algorithms. The algorithm that I'm going to talk about the most today is modularity maximization, and there's a couple reasons for that. One is that it's arguably one of the most common in network science that's used. The second reason is that it actually has some really nice internal structure that you can change to make it more relevant for a brain, or more relevant for a social network, or more relevant for a material. And I'll talk a little bit about what those pieces are. So the equation that you see up here is for Q of a single matrix. So Q is the modularity index. And what you're trying to do is you're trying to maximize the difference between A, which is your connectivity matrix, we also call it an adjacency matrix, and then some null model, which is Pij. So that null model can take many different forms, and I'm actually going to talk about a couple forms later, and how you would choose that null model to make it specific to brains, for example, versus something else. So what you're doing is that you're maximizing the difference between your adjacency matrix and the null model, subject to the assignment of nodes to communities. So what you're trying to do is basically sort nodes into communities so that you maximize the difference between your real data and the null model. The important parameter I wanted to also point out in here is that little gamma that's out in front of P. So that is a tunable parameter that sits outside of the null model and enables you to tune the size of the communities that you detect. So if you just pull down modularity maximization from a website, it will probably have a gamma of 1, which is sort of the default that's often present in these algorithms. So you will get maybe 3 or 4 communities inside of your brain network, and you might wonder, well, why did I find 3 or 4 when Steve can find 10 or Thomas can find 17, right? Well, the reason is that there are, well, number one is that there are different algorithms, but number two, each algorithm also has tunable parameters. And there's some interesting questions about how do you tune that if you don't know the underlying structure in your data, and I'll get to that in a second. But just a note to that, it's important to understand that this maximization algorithm does in fact have a tunable parameter that lets you choose roughly the size of the number of communities that you detect. Okay. So then that's what you would do with a static graph. How do we deal with dynamic networks? So you've heard a little bit about dynamics over the last couple of talks. The general idea, if we had to write it down in a little picture, is that we'll take imaging data from the brain. This could be fMRI, it could be MEG, it could be EEG, it could be ECOG, it could even be calcium transients from neurons. Okay, and then what you do is that you define time windows, for example, and these could be overlapping time windows, or they can be independent time windows. I'm leaving that actual construction up to you. I'm not going to talk about the nitty-gritty of that. There's all sorts of really interesting methodological questions there too. But assume that you've created your time windows. In each time window, you then calculate a functional connectivity matrix. And again, this can be a Pearson correlation matrix. It could be a coherence. You could have used wavelets to clean up the data first. It can be with and without motion, artifact, rejection, everything else, or it could be the tangent space estimates, or it could be a partial correlation. So I'm currently going to be agnostic to what you did to create your functional connectivity matrix. I'm just going to say you have a matrix in front of you, okay? And in fact, you have a set of matrices in front of you that are from ordered in time. So what do you do with them then, right? A really important fact about this system is that those networks didn't happen in isolation from one another. They actually happened in order. So you don't necessarily want to deal with each of them independently because they're not independent samples, right? So how do we deal with the fact that these are not independent samples and therefore shouldn't be treated as if they're independent samples? Well, what we do as one solution is to treat it as a multi-layer graph. So what's a multi-layer graph? A multi-layer graph is where you have a graph or a network in one time window and you connect it up to the network in the next time window, and then you connect that one to the network in the next time window and the next. So what I'm showing you here is a little toy graph that's 4 nodes and 4 edges. It's the little box that's in the center. And then what I'm showing you is that I've added colored edges that connect up one node in one time slice to itself in the next time slice, and then to itself in the next time slice, and etc. So what this is, the fact that this is hard coding is that their, let's say, visual cortex or primary, V1 in time window 1 is the same as that node in time window 2, which is the same as that node in time window 3. Okay, so this is hard coding regional identity, and it's also taking into account the fact that these are not independent samples. Okay, so this is what's called a multi-layer graph. It turns your adjacency matrix into a 3-dimensional object, so it's an adjacency tensor now, and it allows us to inform solutions in one layer with information from neighboring layers. What's nice about that is, from a statistical perspective, is that even though each of your windows may be quite noisy, by linking them up together, you have the opportunity to capitalize on that information to better inform your solutions in a single layer. So it's a way of denoising in some sense. and can enhance your statistical power to observe changes over time. So once we have that multi-layer structure, what do we do with it? Well, again, we'll do a modularity maximization, but now the modularity maximization will take into account the fact that this is an adjacency tensor and not an adjacency matrix. So the simple thing that hopefully you notice is that now A, what used to be your adjacency matrix, has 3 indices: the connectivity between node I, node J in layer L, or time window L. Okay, so now there are 3 pieces of information that tell you about that edge. But otherwise, the structure is roughly the same. The other really important addition here is that those identity links that link up V1 with itself in the next time slice, you can assign a weight to them. And that weight can be 0, that weight could be 1, that weight could be infinity. So that parameter is actually called omega, and that tunes the relative stickiness of the layers to one another. So you can imagine if you tune omega high, you're going to have very sticky layers, and your solution across that entire time will be almost identical. And if you tune omega down, then the layers are not very sticky with one another, and your solutions will actually vary a lot. So omega also enables you to identify different dynamics over different time scales. And that's important. So over the last couple of years, we've defined a couple different statistics on that changing modular structure. The first one is what we called flexibility. So that is counting up the number of switches that a brain region makes to different modules over time. So maybe a brain region sits in one module in the first time window, but then it changes to another time window or another module in another time window. So what you can do is that you can count up how many times does this brain region switch modules, and then divide that number by the number of possible switches the brain region could have made. That's the flexibility. But importantly, that doesn't really distinguish between 2 really drastically different types of dynamics. Let's say that you have a brain region that pops back and forth between 2 modules and just goes back and forth every other time window between those 2 modules. That would be a highly flexible region, right? However, what happens if that same region was actually moving between 10 different modules? That's completely different from a cognitive perspective. It's also completely different from potentially an artifact perspective, right? So it's important to distinguish between those 2 potential dynamic phenotypes. So the second statistic that we quantified is promiscuity, which is the number of different modules that a node associates with. And then finally, we also defined this measure called cohesiveness, which asks the question of, is a brain region moving to a new module all by itself, no other nodes are coming with it, or is it moving in concert with several others? So let's say you have a single brain region. Is it moving by itself to a new community, or does it have 2 or 3 other nodes in its community that are also moving to a new community? If you're moving collectively with other nodes, that's a cohesive movement, and so we can measure that. What's really interesting about these additional measures is that they become more and more sensitive to individual differences in behavior. So we actually find in this Telesford paper that when you look specifically at cohesive movements, that's a much better predictor of individual differences in learning than if you look at the independent movements, which might be more related to noise. Okay, and then here's just a couple different examples of how we have used that notion of flexibility over the last couple years. We've particularly been applying it, the large majority of studies are in task-based data, and specifically task-based fMRI data. In the first study, we looked at individuals learning a motor skill over first 3 days and then 6 weeks with multiple scanning sessions throughout that training period, and we identified changes in this modular structure as people were training. And we found that changes in flexibility were correlated with individual differences in learning over that extended period of time. We also showed that if you measure flexibility during NBAC performance, it's positively correlated with NBAC accuracy, and it's also correlated with cognitive flexibility as measured by a Trails B score, suggesting that it might actually be more related to higher order executive functions rather than learning specifically. We've also shown that it's related to reinforcement learning rate. So if you're actually using information over a long period of time to make a decision, you have higher flexibility in your brain than if you're using information over a short period of time to make a decision. And then finally, work from Rick Bessel in my lab has shown that flexibility is also related to mood over multiple days of imaging. So higher levels of positive attitude are related to higher amounts of flexibility. And that's from a single individual imaged over 100 days. On the bottom here, what I'm showing you is that you can also modulate flexibility with drugs. So taking dextromethorphan, which is an NMDA receptor antagonist, increases your flexibility. And that suggests that there is potentially this role for excitatory and inhibitory balance driving this whole brain flexibility. We also see that flexibility is an intermediate phenotype of schizophrenia, which is thought to be driven to some degree by an alteration in the excitatory inhibitory balance. So this is the Braun 2016 Proceedings of the National Academy of Sciences paper. Both of these two studies are in that paper. So that suggests to us that this is something that is related to underlying neurotransmitter level drivers. So now the question is, what if we would want to extend some of these same techniques to multimodal or other data? So here what I have is a graph of, again, a multi-layer network, but with two different types of coupling. So on the top, what you're seeing is what I call ordinal coupling. That means one network is connected to itself in the next time window, right? But if you have something that's not temporal, then it's not necessarily right to order them, right? So let's say you have 200 subjects. You don't necessarily want to string the 200 subjects in a row, because how would you order them? What's the right way of ordering 200 subjects? You don't necessarily know. So in that case, what you would want to do is what's called categorical coupling, which is where you link every person to every other person, or every network to every other network. And that's shown on the bottom. That's called categorical coupling. So for that, you could use that for looking across individuals, for looking across tasks, which again would not be ordinal, that would be categorical, right? For looking across imaging modalities, gender, race, I put hair color and eye color, that's obviously you're probably not going to do that, but the idea is anything that doesn't have a natural linear order to it, you would want to use a categorical coupling instead. And I put a couple references down at the bottom of papers that have used the categorical coupling of the multilayer modularity quality function to look at dynamic community structure in either across task questions or combining diffusion imaging and fMRI. So truly a multimodal problem. Okay, so what are some methodological considerations? That's what we can do, and I'll give you code for it in a second. How do we do it right, and what should we be thinking about? The first thing that you should be thinking about is that actually maximizing the modularity quality function is NP hard. It's a really nasty problem. There are various heuristics to do it, some better than others. The actual landscape of the modularity quality function is really bumpy. And the top of the maximization it does have a plateau often rather than a peak, and the plateau is also extremely bumpy. So what that means is that you can get many solutions that are really similar to one another, but a teeny bit different. So what do you do about that? The thing that you do about that is that you actually should run modularity maximization multiple times. We usually do about 100. This is going to depend on the size of your network, etc. And then after you do that, then you should only report statistics that are consistent across all of those optimizations. You don't want to cherry pick one optimization and just report that one. The other important point to make here is that the bumpiness of the landscape is actually dependent on the size of your network. So larger networks have bumpier landscapes. Smaller networks have less bumpy landscapes, so smaller networks are good for this particular case. And if you have a binary graph, so if you've thresholded your functional connectivity matrix to make it zeros and ones, that increases the nastiness of the modularity landscape. Whereas if you have weights on all of your edges, it smooths the landscape significantly. So these are two reasons to choose not millions of nodes, and to maintain all of the weights on all of your edges when using this approach, and not threshold. Okay, so then the second question is, do you remember I pointed out this null model, the PIJ, and I said this is a null model where you're comparing your true data to the null model, and what you want to do is to maximize the differences between them. So a really common null model that people have used before is what's called a Newman-Girvin null model. That's defined as, in binary graphs, it's the degree of node I times the degree of node j divided by 2 times the number of edges in the graph. That's the most common. However, that doesn't have any sort of biological logical notion of anything in it. So what you can do is actually inform that null model with other facts that you know about the brain. For example, how distant two brain regions are, and the fact that two brain regions that are farther away from each other have a lower probability of connecting than two regions that are close by to one another. So that is an alternative null model to include spatial information inside of this maximization approach. And there are two citations at the bottom which describe some of those additional null models. You also probably want to be thinking about what I call post-optimization null models, which means, let's say you identify your modules, you estimate the flexibility or the cohesiveness. Now, what do? Well, you want to determine that that's different than what you would anticipate in appropriate dynamic network null models. What is an appropriate dynamic network null model? There are at least 3 that I'm going to show you right here that are interesting and relevant. The first one is to actually, we call it a connectional null model. That means you want to randomly reassign the edges inside of your graph in each of the windows or instances. The nodal null model is where you want to change those identity links that make the multi-layer graph. So instead of connecting V1 with V1, you're going to connect V1 with DLPFC or something else randomly chosen out of the hat. And then the third null model is a temporal null model where you actually randomly permute the order of graphs inside of your multi-layer structure. So instead of having time window 1 next to time window 2 next to time window 3, now each of those are randomly interspersed among each other. So you've destroyed any low frequency changes in the network organization that are present. What you want to do is to show that any of the statistics you've quantified in the real data are different than these null models. There are also important questions about parameter choices. I told you that omega is the stickiness of the multi-layer structure, and I told you that gamma tunes the size or number of communities. So an open question is, how do you pick those numbers? What you can do is that actually you can quantify something like the modularity index. Look at the top right here. Quantify the difference between the modularity index in your real data and in one of these null models across that whole gamma omega plane. So you're doing a parameter sweep across those two variables. And what you can see in this case, for example, is that there's a clear peak where there's a maximum difference between your data and the null model in that two-dimensional plane. And so that's a really nice data-driven way of choosing both omega, which is the stickiness of the graph, or the identity links, and the gamma value. The other point I wanted to mention, even though I told you that I wasn't going to really get into a lot of the details about choosing time windows, I think it is important to realize that there's a really large, beautiful set of work that's been addressing that question, and to be aware of it. And so when you do choose time windows, to make sure that you understand this literature as well. So you need to consider the frequency band over which you wish to study functional connectivity. There's a really beautiful paper from Dimitri van de Ville and Leonardi in 2015 that I very highly recommend. You may also want to identify time points of different lengths directly from the data. So you might imagine that time windows are all the same length. That would be a natural maybe place to start. But the brain may actually be having states that are of different lengths. And so therefore you may wish to have a short time window here and then a longer time window that's relevant for the dynamics of that particular task. And if that's true, then you want to be able to identify change points in the dynamics directly from the data. And there's this beautiful work in 2015 in Frontiers of Neuroscience that I really highly suggest as well. There's also work from us that considers that time window length does enhance or decrement your sensitivity to individual differences. So keep that in mind as well. And then finally, an admission that there actually is a world beyond modularity and beyond community structure as well. And I want you to be aware that that's true as well. So in particular, modularity and other community detection techniques assume that what you have in your data is the top right on this slide, right? Where you have modules and they're densely interconnected within them and sparsely connected between. However, there's a lot of other beautiful structure. There's core periphery structure, there's bipartite structure, there's, maybe your data is like the bottom right, which has a bit of all 3. And if that's the case, then stochastic block models are what you should be using rather than modularity maximization. Last point, I know I'm out of time, is that we've also been assuming that there's one graph for every time window. That's an assumption, and it's a simplification. right? It's very possible that actually in every time window, there are 10 different graphs that are present, but they're expressed to differing amounts. So what you might want to do is to identify a basis set of graphs that vary in their expression over time. So now it's not one network per time window, it may be 10 networks per time window that vary in how much they're expressed as a function of the task. And we show in these papers that you can do that with non-negative matrix factorization, and that you can identify subgraphs that are in some cases quite different from modules. All right, here's the code. And I'm going to leave it up and see if there's any questions, if we have time for questions.
Okay.